All right, next up, we have simple harmonic oscillation, SHO. I like to keep it simple. What with the whole simple? I didn't actually plan that. Now I feel bad because it's a terrible pun. Of the important equations, one of the first ones I like to arm you with is that T, capital T, our period, how long it takes to complete one cycle, is equal to 2 pi divided by omega. Now, one of the things that we did in my class, as opposed to some of the other approaches to physics, is I dealt almost solely with omega, as opposed to frequency, the little f, which is one thing that more people are used to. And when we get to modern, we dealt more with frequency f because it was a little bit easier. But the reason why I always dealt with omega is for the following. There are some fundamental reasons why these guys show up a little bit more. Omega, our natural frequency for a pendulum, is equal to the square root of g over L, where g is the local acceleration due to gravity. So again, and this is one of those circumstances where I could take a grandfather clock, which is something that uses a pendulum to keep track of time. I could take a pendulum up to the moon, I could put it on Mars, I could put it anywhere. Doesn't matter, I could still put in these values and find exactly what its natural frequency is going to be. I would just use a different little g. L is going to be the length of the pendulum arm. So basically, a pendulum is usually something that you've got hanging like this and you put a mass on it. L is going to be how long it is. For the surface of the Earth, if you have L equal to right at about a meter, you will end up with a period of about 2 seconds. I'll double check that, but that should be about right. Because that's one of the reasons why on the grandfather clock, it's about 1 meter long, because as it goes up, and it goes back and forth once, so it goes from here over to here, I should say. So half of its full cycle, one cycle is coming back to where it starts from. So I go over here, that's half a cycle, that's 1 second. And then it comes back, that's 2 seconds. And so it's rigged up such that when it gets to the edges, tick, 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 tick. And that's how it keeps time. And that's one of the ways that I remember that a length of about a meter, a little bit less than a meter, will get me a period of 2 seconds, not 1 second. Now, to be my luck, I'm completely wrong on that and remembering it incorrectly. It turns out I've been doing most of these videos kind of back to back, and so I'm running out of room in my brain. Omega for a spring, which is one of the others that we are dealing with. Square root of k divided by m, where k is our spring constant that describes how stiff the spring is, how floppy it is, that sort of thing. M is the mass that we have attached to that spring, and so we've got a spring here, and we've got a mass m. We'll have a certain stiffness of that spring, k. Remember, spring constants are measured in newtons per meter. And it depends on what springs you're dealing with, but you're probably going to be dealing with something on the order of about 100 to 1,000. You can have things that are springs that are stiffer than that. You can have springs that are floppier than that. A slinky, I think, is at something like 20 newtons per meter or something. It's a very low number, a very floppy spring. And then some of the springs that you would use like on a screen door to try and pull it closed, they're going to be up in the several hundred range, maybe up to 1,000. And so really, really stiff springs, the type of thing that you would use for industrial purposes, they can get up much higher than that. But most of the ones that you're going to be dealing with, probably going to be the 100 to 1,000 range. Just to give you an idea for what the usual values are. All right, so we've got that. We've got our springs. One of the main ways that we end up solving things related with our simple harmonic oscillators is energy. I told you energy was kind of a key thing for understanding stuff. The total energy for a simple harmonic oscillator is equal to 1/2 k A squared, where A is your amplitude. Amplitude is how the furthest point that you get from your equilibrium position. We'll talk about equilibrium in just a moment as one of the concepts. And the final thing that we've got equation-wise, our position is going to be A, which is our amplitude, times sine omega t. Now I also went through and I told you that if we've got, normally this can be a sine or a cosine, it depends on when you look at your graph or how you start your stopwatch. Sine is going to be if it starts off like this. If you have something that starts off like this instead, then this is cosine. You can also have them where they start off going down underneath, and that'll be negative sine. Or start off here, and that would be negative cosine. Okay? But the general form looks like this, and related to that, your velocity is going to be a omega cosine omega t. These are things that it doesn't hurt to be familiar with at the very least. You get this mostly by doing some brief calculus. So if you've had some calculus, you can see that it's just kind of chain rule here. And then finally, your acceleration in this case is going to be negative a omega squared sine omega t. Okay? So, but the main one is be familiar with the fact that they maintain the form of a sine function or a cosine. And that you can find your omega here. You can look at the chart and you can actually get a measurement of your period, and with this relationship you can convert that over to your angular frequency, among other things. Now, a couple of the things that we want to talk about with this are going to be equilibrium. That's going to be the first one we're going to talk about. Equilibrium is kind of the middle of our rotation in each case. It is defined as where our force is equal to 0. Okay? So oftentimes it's going to be in the exact middle. It's going to be where x equals 0 whenever we're dealing with springs, for instance. Okay? But whenever you're looking for equilibrium positions, it's where the force on it is actually equal to 0. You will also find that with these equations, that means if your force is equal to 0, all of your forces, that means your acceleration is equal to 0. And by the same token, because these are both sines, you're going to find that they have a tendency for your position to also be 0 at that point. Now, big things you want to keep track of are when your variables, your position, your velocity, and your accelerations are going to be maximums. Okay? So, when you're in the very middle at the equilibrium position, your force is going to be 0, so that tells you your acceleration is going to be 0. That doesn't sound maximum to me. That one's a minimum. And we also know that we're at x equals 0, so our position is also going to be at a minimum. Okay? Now, your velocity is actually going to be at a maximum. You can kind of tell because when your sine value is at a minimum, your cosine has a tendency of ending up at a maximum, where like sine of 90 degrees is 1, cosine of 90 degrees is 0. And sine of 0 degrees is 0, and cosine of 0 degrees is 1. They kind of have that weird trade-off. When one's really big, the other's kind of small. Your velocity is actually going to be highest here when you cut through equilibrium. Conversely, and so if I were to draw this out, I could have it where we've got the spring, we've got a mass here, and this will be our equilibrium position, x equals 0. Our acceleration is going to be equal 0 here, and our velocity will be maximum. When you get all the way out to the edge, where this is our amplitude, A, our position is going to be our amplitude, and this is going to be the largest it gets. That's going to be our maximum position, because now it's going to come back in this way and then go over to the negative. It'll go all the way to negative A and then come back over. Our acceleration is going to be maximum because our force is going to be greatest there. We're the furthest out, and now it's going to push us back in here. And that's the point where our velocity is actually going to be equal to 0, because we've gone as far as we're going this direction, and we're about to start heading back the other way. So if we used to be going that way, and in just a moment we're going to be going that way, we've got to come to a complete stop so that we can turn around. That's a crash course in dealing with that. The other things that you want to deal with are the things that set this sort of thing up are called restoring forces. That's one of the reasons why these are usually modeled by springs. I mentioned it before when we talked about the forces, that the force of a spring has that negative sign in there. It means if you move one way, this way, out to the right, your force is going to be back to the left. That's what we call a restoring force, because it keeps trying to restore the thing back where it came from. If I move off to the left, my force is going to be to the right. So it's going to constantly try and return the thing right here in the middle, a restoring force. Now, normally we'll actually model those as springs in one way or another, so springs are kind of the main way that we approach simple harmonic oscillators. The final thing that we'll talk about is resonance. And resonance is kind of the natural frequency, driving something at the natural frequency that it has. And the main thing that I used to get that idea across was a swing set. If you want to get higher and higher, you start off where you're like this. If you want to get higher and higher, you have to kick your feet at just the right time. You can't just go out there and kick them all crazy like. You're not really going to get very far. You have to push your feet at the right times, and that's actually the resonant frequency. You're taking advantage of resonance, where now when you get up to the very top, you're doing what you need to, and now you're adding a little bit of energy each time, and as a result, you get higher and higher. You go faster and faster. Now, in reality, you're going to run into a situation where as you get going faster and faster, you're going to have an increased drag force, and that's why you never really kick enough to make yourself go all the way around. But resonance is a very important concept. In my class, I showed you a couple different things that you could get an idea of the usefulness of resonance. One is opera singers shattering glass, if that is actually something that happens. I never get a straight story on that. However, ones that do actually apply are things like the tides in the Bay of Fundy. Go ahead and look that one back up. But it has things set up just right where the tides come in at a resonant frequency, and you actually have the tides raise up and drop back down by an incredible amount every day. Well, actually, at the frequency of the tides, so several times a day it would seem. And then there are a few others that we actually went through and we looked at for the idea of resonance. But one of the key things to think about is the swing set. Okay? So, that's an overview of simple harmonic oscillation.